Hi everyone, I am Mrs.S.ARULJOTHI, Assistant Professor of Physics, A.D.M.COLEGE for Women, NAGAPATTINam. Today's session we are going to learn communication physics. Communication physics is nothing but it's one of the applied branch of physics. It deals with various kinds of communication system. A communication system is collected of individual telecommunication networks, transmission system, relay stations, tributary station, and terminal equipment usually capable of interconnection and interoperation to form an integrated whole. The components of communication system serve a common purpose, are technically compatible, use common procedure, respond to control, and operate in union. This is one of the communication system pictures. The word communicate refers to pass, and the act of communicating is termed communication. This is the broad sense. The term communication refers to the transmission of information from one place to other. Later, the use of satellite and fiber optic made communication even more widespread with an increasing emphasis on wireless, computer, and other data communication. Presently, in the early period of 21st century, we live in a modern society where several electrical modes of communication are at our disposal. Some of these include landline, telephone, set, fax, machine, mobile phone, computer with the internet, and personal digital assistant. Due to minimization, most of these communication aids have become gadgets in the hands of the current generation. The different steps involved in transmission of information, origin of information in the mind of the person who wants to communicate, generation the message signal carrying the information, converting the message signal into electrical form using a suitable transducer, transmission of the perceived message signal to the desired destination, reception of the perceived message signal at the desired destination. Thus, the basic issues involved in the above outlined steps, independent of the type of communication system, is the first step towards making an entry into the electrical communication discipline. The several communication systems like telephony, radio broadcasting, television broadcasting, radar communication, satellite communication, fiber optic communication, computer communication, and wireless communication can be studied. First one, wave propagation. Wave propagation is any of the way in which waves travel with respect to the direction of the oscillation relative to the propagation direction. We can distinguish between longitudinal wave and transverse wave. For electromagnetic waves, propagation may occur in a vacuum as well as in the material medium. Other wave types cannot propagate through a vacuum and need a transmission medium to excite. Fundamental electromagnetic wave. Electromagnetic wave are energy propagated through free space at the velocity of light, which is approximately 300 meters per microsecond. Visualize standing on a bridge overlooking a calm body of water. If you were to drop an object into the pond, you would see this energy process in action. As the object traveled downward, there would be a path of bubbles generated in same direction vertical as object. But there would also the circular wave pattern radiating from the point of impact and spreading horizontally across the body of water. This is one of the electromagnetic wave pictures. Another one, electromagnetic wave action. This action can be related to the term power density. If power density is defined as a radiated power per unit area, it follows the power density is reduced to 1/4 of its value when distance from the source is doubled. Also, the direction of electric field, the magnetic field, and propagation are mutually perpendicular in electromagnetic wave. This is theoretical assumption which cannot be waves or invisible. Next one, free space propagation. Since no interference or uptaxal are present in the free space, electromagnetic wave will spread uniformly in all directions from a point source. The wavefront is thus spherical of cross section. To simplify the description even further, rays are imagined with the radiate from the point source in all directions. They are everywhere perpendicular to the tangential plane of the wavefront, just like the spoke of wheel. At a distance corresponding to the length of ray, rho, the wave has a certain phase. It may have left the source at an instant when its voltage and current were maximum in the circuit of the source. If the distance traveled correspond to the exactly 1,00,025 wavelength, the instantaneous electric and magnetic intensities are at the moment zero at all such points. If power density is defined as radiated power per unit area, it follows that power density is reduced to 1/4 of its value when distance from the source has doubled. It's seen that power density is inversely proportional to the square of the distance from the source. This is inverse square law which applies to all radiation in free space. Starting this mathematically, we have rho is equal to Pt by 4 pi r square 2, where rho power density of the distance, power density or distance from an isotropic source. T1 transmitted power. The electric and the magnetic field intensities of electromagnetic waves are also important. The two quantities are direct counterparts of voltage and current in circuits. They are measured in volts per meter and ampere per meter. The characteristic impedance of the medium is given by L squared, L equal to root of mu by epsilon, where mu permeability of medium, epsilon electric permittivity of medium. For free space, mu equal to 4 pi into 10 power minus 7. This value 1.257 into 10 power minus 6. Epsilon equal to 1 by 36 pi into 10. This exactly value 8.854 into 10 power minus 12. It will recall that permeability in the equivalent of induction and the permittivity is the equivalent of capacitance in electric circuit. Indeed, the units used above are remainder of this. It is now possible to calculate value for the characteristic impedance of free space. Next one, surface wave propagation. I mean ground wave. Ground wave progress along the surface of the earth and as previously mentioned must be vertically polarized to prevent short circuiting the electric components. This is made up by energy diffracted downward from the upper portion of the wavefront. Since it shows that the maximum range of such a transmitter depends on its frequency as well as its power. Next one, field strength at a distance. Radiation from an antenna by means of the ground wave gives rise to a field strength at a distance, which may be calculated by the use of Maxwell's equations. This field strength in volt per meter of the transmitting antenna. Epsilon equal to 120 pi HTL by lambda d. Ground wave propagation picture. If a receive antenna is now placed at this point, the signal will be volt. P is equal to 120 pi HT HR L by lambda d. 120 pi equal to characteristic impedance of the free space. HT efficient height. HR efficient height of the receiving antenna. I equal to antenna current. D distance from the transmitting antenna. Lambda wavelength. If the distance between two antennas is fairly long, the reduction of field strength due to ground and atmospheric absorption reduces the value of the voltage received, making it less than it is possible to calculate the signal strength reduction, which results altogether too many variables are involved to make this worthwhile. Such variables include the salinity and resistivity of the ground or water over which the wave propagates and the water vapor content of the air. Another one, sky wave. It had been suspected that ionization of the upper parts of the Earth's atmosphere played a part in the propagation of radio waves, particularly at high frequency. The atmosphere receives sufficient energy from the sun for its molecules to split into positive and negative ions. They remain that ionized for long periods of time. He also showed that there were several layers of ionization at different heights which reflect back to Earth the high frequency waves. The ionosphere and its effect. The ionosphere is the upper portion of the atmosphere which absorbs large quantity of radiant energy from the sun, becoming heated and ionized. There are variations in physical properties of the atmospheric such as temperature, density and composition. The most important ionizing agent are ultraviolet and alpha, beta, gamma radiation from the sun as well as cosmic rays and metras. The D layer is the lowest existing at an average height of 70 km with an average thickness of 10 km. The degree of its ionization depends on the attitude of sun above the horizon and thus it disappears at night. It is the least important layer from the point of view of HF propagation. If reflection wave and absorb waves to certain extent. The sky wave propagation, Earth, radio power, home, ionosphere. Next one, the E layer is the next in height, existing and about 100 km with a thickness of perhaps 25 km. Like the D layer, it all but disappears at night. The reason for this disappearance is the recombination of the ions into molecules. This is due to absence of the sun, when radiation is consequently no longer received. The main effect of the E layer are to aid surface wave propagation a little and to reflect some waves in daytime. The Fi layer exists at the height of 180 km in daytime and combined with the layer at night. Its daytime thickness is about 20 km. Thus, the main effect of the layer is to provide more absorption for HF waves. The F2 layer is by far the most important reflective medium for high frequency radio waves. Its approximate thickness can be up to 200 km and its height ranges from 250 to 400 km in daytime. At night, it falls to height of about 300 km where it is combined with the F1 layer. Travel radio waves at different angle incidence. When the angle of incidence is made quite large, as for ray 1, the sky wave returns to ground at a long distance from the transmitter. As this angle is slowly reduced, naturally the wave returns to ground at a long distance from the transmitter. As this angle is slowly reduced, naturally the wave returns closer and closer to the transmitter by rays 2 and 3. It may be bent noticeably as for rays 4 or only slightly as for ray 5, but a distance further than the return point of ray 3, a ray such as this ray 6. This is the ray deviation. Space waves. Space waves generally behave with the merciful simplicity. They travel in straight line, however, since they depend on line of sight condition. Space waves are limited in their propagation by the curvature of the Earth, except in very unusual circumstances. Thus, they propagate very much like electromagnetic waves in free space. Behavior is forced on them because of that wavelength are too short for reflection from the ionosphere. And because the ground wave disappear very close to the transmitter. Radio horizon. The radio horizon for space waves is about 4/3 as far as the optical horizon. The beneficial effect is caused by the varying density of the atmosphere and because of diffraction around the curvature of the Earth. The radio horizon of an antenna is given with good approximation by the empirical formula dt equal to 4√ht. dt is the distance from transmitting antenna, kilometer. ht, height of transmitting antenna above ground, meter. The same formula naturally applies to the receiving antenna. Thus, the total distance will be given by addition as the empirical formula. Another one, microwave space wave propagation. All the effects so far described hold true for microwave frequency, but some are increased and the new ones are added. Atmosphere and absorption and the effect of perception must be taken into account. The change in refractive index is normally linear and gradual, but under certain atmospheric conditions, a layer of warm air may be trapped above the cool air, often over the surface of water. Microwaves are thus continuously refracted in the bending down takes place as they are propagated around the curvature of this earth for distance which sometimes exceed 1000 kilometers. The main requirement for the formation of atmospheric ducts is the temperature inversion. This is an increase of air temperature with the height instead of the usual decrease in temperature of 6.5 degrees Celsius with the standard atmosphere. This is one of the super perfection in the atmospheric duct. Next one, tropospheric scatter propagation. The tropospheric scatter propagation is means beyond the horizon propagation of UHF signals. It uses certain properties of the troposphere, the nearest portion of atmospheric. Then properties, the two directional antennas are pointed so that the beams intersect midway between them above the horizon. If one of these is UHF transmitting antenna and other UHF receiving one, sufficiently radio energy will be directed towards the receiving antenna to make this useful communication system. The best frequency which is are also the most often used are centered on 900, 2000 and 5000 megahertz. Even here the actual propagation for forward scatter to signals incident on the scatter values is very tiny between 60 and 90 decibel or 1 million to 1 billion of the instant power. Another one, practical consideration. Although forward scatter is subjected to fading with a little signal scattered forward, it is nevertheless a form of very reliable method of over the horizon communication. It is not affected by the abnormal phenomena that afflict HF skywave propagation. Accordingly, this method of propagation is often used to provide long distance telephone and other communication links as an alternative to microwave links or coaxial cables over rough or inaccessible terrain. This is the tropospheric scatter propagation. It has been found in practice that the best result are obtained from the troposcatter propagation if antennas are elevated and then directed down towards the horizon. Also, because of the fading problems, diversity system are invariably employed with space diversity more common than frequency diversity. The two antennas at either end of the link separated by distance somewhat in excess of 30 wavelengths. Thank you.